Okay, so for our last clip now, we're going to talk a little bit more about how we travel these molecules of respiratory gases in our blood. So oxygen, when we think about oxygen transport, oxygen and hemoglobin is the transport mechanism for oxygen. If we look at a hemoglobin molecule, it has four spikes on it, and it's the iron portion in which it carries. But there, just imagine this sort of round ball with these four spikes sticking out, and oxygen loves them, so it jumps on these little spikes and travels through the blood on it. This is a great thing because it's an unstable bond. So as soon as the oxygen gets to a place where there's an area of low oxygen or they're hypoxic tissues, then the oxygen jumps off and goes into those cells by diffusion. So why does oxygen go in? Well, a couple of things. The levels of carbon dioxide. So if it's a high serum carbon dioxide, then our oxygen will want to go in because those are the principles of diffusion. The pH, the more acidic an area is, and that fits with the carbon dioxide, the more oxygen is needed in that area. And finally, the temperature. If the temperature of the blood is high, it's indicative that there's been energy being made at the cellular level. So that in turn goes with the other two. So increased levels of carbon dioxide, pH, and blood temperature. As the carbon dioxide gets released during intense skeletal exercise, because oxygen is used to make ATP, we see the pH drop and an increase in temperature correspondingly. So just taking a look at this picture, we're just going to just look at the principles of how things happen. So here's the blood coming from the heart. Okay, it's going to come by the pulmonary artery. This is the alveoli, and this would be the pulmonary vein. And this is the capillary, actually, but this is the source of it. Okay. So as you can see, and don't worry about these numbers so much, but just know that everything moves from high to low. So our blood coming back to the lungs is getting refreshed, so it's going to be a high concentration of carbon dioxide versus what we have in the lung, and vice versa. Our oxygen will be high, and it'll want to come into the capillary because it's low. So looking at this picture here, this helps us show you the molecules of hemoglobin and how it has four little spikes on it. So you see how these are coming back and there's maybe three on some of them, most of them by the looks of things. As the oxygen is taken from the alveoli into the capillary, it's now got four and it moves along and it keeps moving until it comes to a spot where it needs oxygen, and then the little oxygen molecules flip off and go into those cells. Carbon dioxide transport, it diffuses out of the cell because again of diffusion, high to low, and it needs to be removed from the body. Now it does that in one of three ways. I'm just going to go to a picture that we have here. Sorry, it's right at the end, so I'm going to have to flip back there. There we go. So here's our cell full of carbon dioxide. So it can happen by three ways: being dissolved in the plasma as carbaminohemoglobin, and also just free floating as bicarbonate ions. So the least amount of carbon dioxide directly floats in the plasma, okay? And that's about 7 to 10%. The remainder go inside the red blood cell and we get some chemical reactions happening. So the first one, the carbon dioxide goes into the red blood cell. 20 to 30% of our carbon dioxide is transported in a molecule we call carbaminohemoglobin. Sorry, that's kind of a mouthful there. And it combines with the protein portion and not the iron, because remember, iron is reserved for our oxygen. So we don't have any competition for these binding sites. And so what you see then is carbon dioxide plus hemoglobin equals carbaminohemoglobin. Okay. So that's 20 to 30%. The largest percentage of our carbon dioxide is converted to bicarbonate ions, which transport in the plasma. So just take a look now. I put all these equations in your notes, but if you can watch the cursor. So here's the carbon dioxide. It slips inside the cell, okay, and it combines with water, forming something called carbonic acid, which we talked about already when we talked about acid base. So here we go. There's my cursor. Carbon dioxide and water to become carbonic acid, which then dissociates to become hydrogen and bicarbonate ions. The hydrogen teams up with hemoglobin inside there, and the bicarb slips outside the cell. There's an enzyme in there that assists all this conversion. Okay, so now this here is going to travel all along. So the hydrogen again is going to team up with this hemoglobin, and the bicarb is slipping out inside of the into the plasma. So it travels now to the lungs. So we get to the lungs, and what happens? We reverse it all. We have some enzyme activity coming, but here we are. Okay, so first of all, if it's just been dissolved in the plasma, it goes out like that. If it is part of the bicarb slips back in, finds the hemoglobin, releases the hydrogen. They join up, become carbonic acid, separate to become water and carbon dioxide. We get rid of the carbon dioxide into the lung and we exhale it. Or we could do a couple of other things. We could our water might be, when you breathe out and it's cold and you can see your breath, so we always lose a little bit of water with our breath. Or maybe we use the water in some other kind of chemical reaction. So if you look here, we said the piece that combines with carbanoaminohemoglobin, it separates, okay, and the carbon dioxide slips out. So those are the three ways it can travel: by itself, as bicarbonate ions, or with the hemoglobin portion. So remember that we talked about our hemoglobin molecule carrying oxygen. When it leaves, I'm just going to slip back now. When the blood leaves the pulmonary circuit, or it's leaving the lungs, it's 97 to 100% saturated. Once it goes all the way around the body, it's completed the systemic circuit. It still is 75% saturated. So oxygen, we measure it in our through pulse oximetry, and some of you may have had the opportunity to do that or had it done yourself, where you put the little clip on your finger, and what it's measuring is how well is hemoglobin bonded with oxygen, or oxygen, I should say, bonded with hemoglobin. Another way, and we'll just touch on this because this is really just a little bit of information that we want to have it right now. If we truly want to measure the oxygen levels in your body, what we do is we take an arterial blood sample. So that means a needle has to go into an artery. Usually we use, if you're not in the intensive care unit, we would just use your radial artery. But if you're in the intensive care unit, we'd probably insert a special thing called an arterial line where we could get it all the time. Regardless, what we're trying to do is get an arterial blood sample, because all of our blood samples that we have taken are venous blood samples. I'm going to sneeze here, so I'm just trying to hold it off. Excuse me, sorry. So the pH, what we take then is that arterial blood and we measure the pH. Remember back in chapter 2 or unit 2, I said pH is about acid or base. I think of it like the presence of hydrogen, which represents the acidity of our blood. And we already learned that our blood is 7.35 to 7.45. That's the normal range for it. So below 7.35 is going to be acid, and above 7.35 is going to be base. In order for us to be happy and healthy, our pH needs to stay within that range of 7.35 to 7.45, especially if metabolism is to be maximally effective. Hemoglobin doesn't release its oxygen when our blood is alkaline because it doesn't need to be there, because there must be enough oxygen. Instead, it releases it when our blood is acidic, which makes sense because if you're doing a lot of exercising, then at your cellular level, you're going to have a lot of carbon dioxide because you've been making a lot of ATP. The other thing to think about here is the dangers. If your blood pH falls below 6.8 or goes above 7.8 to 8, your cells will die. Our PCO2, what we're measuring in our PCO2 is the pressure of carbon dioxide in our blood. And as you recall, carbon dioxide is present after we make energy, after we make ATP, and we take it to our blood to get rid of it. Our normal PCO2 is 35 to 45. Our PO2 is 80 to 100. Now that can vary depending on your age. It could be a little bit lower depending on your age. But that's really all we want you to understand about acid-base right now. Acid-base is the measuring of the pH, or the level of acidity in your blood. And the normal range is 7.35 to 4.5. The normal oxygen level is 80 to 100, while the normal carbon dioxide level is 35 to 45. And we've looked at these about how we carry our carbon dioxide. And lastly, then, how the respiratory system assists in the maintenance of pH. The respiratory center, when we talked about pH, we said that our blood buffers are our first line of action there. And they're sort of like sponges that sponge up the acids or the bases and put them into molecules so we can do something else with them, so they're not dangerous to us anymore. The respiratory center in the medulla oblongata assists in the regulation of hydrogen ions by increasing or decreasing our rate of breathing. So in other words, if we have a deep, rapid respiratory rate, we're blowing off CO2. And if we don't have CO2, we cannot make carbonic acid. And vice versa, if our rate is low, then we're holding on to CO2, and if we were alkalotic, that would help bring our balance up to normal. So that ends the respiratory section.